Welcome to Lesson 12 of Applied Physics. This lesson covers circular motion. In this lesson, you will cover the following objectives. Recognize that an object moving in a circular path experiences an acceleration even if that object is moving with a constant speed. Be able to relate the acceleration of the object to its constant speed and radius of circular path. Recognize that the acceleration of an object moving in such a manner is always directed toward the center of the circular path. Understand what a centripetal force is and why it is pointing toward the center of the circle. And solve problems involving Newton's laws of motion for objects moving with uniform circular motion in a systematic way. Here is a flowchart showing topics from uniform circular motion, which hopefully you will read about and understand during your study. Recall that acceleration is defined to be the time rate of change in velocity of an object. This means that any time an object is changing its velocity, it is accelerating. So, what are the distinct ways that an object can change its velocity? We've seen that an object that changes speed experiences acceleration, but is that the only way? What if you are not going in a straight line direction? During a race, a car can change speeds and directions. The first part of this course, we worried about only changing speeds when we had an acceleration. We will now have to consider when the vector quantity of velocity has a magnitude or speed and/or a directional change. If it has a directional change, it will have an acceleration which we will consider to be a centripetal acceleration. An object will therefore experience an acceleration if the speed of the object can change while it travels in a straight line. The direction of travel of the object can change while it travels at constant speed. The object can change speed and change direction at the same time. We have examined situations 1 and 3 in some detail and will return to situation 3 in much more detail later in the course. But the focus of this lesson is that of uniform circular motion. An object moving with this type of motion travels at constant speed along a circular path. An object moving along a circular path is not traveling in a straight line. This means that you cannot use the straight line kinematics formulas developed in previous lessons to describe the motion of such an object. Always remember the limitations of the models we develop in order to avoid the pitfalls that many a student before you has fallen into. You must use the equations for circular motion which we are about to demonstrate derive. Consider an object moving with a constant speed in a circular path. At time t sub 1, the object has a velocity v sub 1. At time t sub 2, the object has a velocity v sub 2. These velocity vectors have the same magnitude since the speed is constant. The acceleration of the object is given by this equation. Thus, the direction of the acceleration is the same as the direction of the velocity change. To get the direction of the velocity change, we note that v sub 2 minus v sub 1 equals v sub 2 plus negative v sub 1, where negative v sub 1 is a vector that is identical to v sub 1, but points in the opposite direction. The vector v sub 1 is subtracted from the vector v sub 2 and shown as a change in velocity. The acceleration of the object points in the direction of the velocity change. Now comes the placement of the acceleration vector. Where does it go? Well, remember that the expression we are using gives the average acceleration of the object. We want the direction of the instantaneous acceleration. We note that if an object moves with an acceleration that is constant in magnitude, the average and instantaneous value are the same only at the midpoint of the time interval. Because this object is moving at a constant speed, the middle of the time interval happens to coincide to the middle of the distance interval. We move the velocity change vector to the middle of the distance interval and relabel it as the acceleration vector. We note that the diagram can be rotated about any angle without changing the relative orientation of the vectors. As we rotate the diagram, we note one important feature. The acceleration vector for this object always points toward the center of the circular path. Such an acceleration that always points toward the center of a circular path is called a center-seeking or centripetal acceleration. It can be shown that the magnitude of the centripetal acceleration of an object traveling in a circular path of radius r at a constant speed v is given by the following. Remember that this centripetal acceleration always points toward the center of the circular path or radially inward. This is a unit vector that points in the radial direction. Then the centripetal acceleration can be written as shown. There is a special time of travel that is of interest when the motion of an object repeats itself. This special time is called the period of the motion and is the time required for the motion of the object to complete itself one time. You can determine the constant speed of an object traveling in a circular path in terms of the time required for the object to complete one circular path. Hence, circumference divided by time is the speed of the object. If an object travels at constant speed, that constant speed can be found by taking the distance traveled and dividing by the associated time of travel. If the time that is used to calculate the constant speed is the period, or time to complete one circular path, then the correct distance to use would be the circumference of the circular path. Recall from our experience with linear motion that speed was the distance traveled divided by the time it took to travel the distance. This was defined as the velocity. Here we have set up the same scenario with the distance traveled actually being the circumference of the circular path and the time being called the time period, which is the amount of time required to make a complete cycle around the circle. We call this value a velocity, the velocity tangent to the circular path, or a linear velocity for the object in circular motion. Here's a problem to work on your own. You will need to look up the radius of the Earth as well as think about how long it takes the Earth to rotate on its axis daily. Using this information and the equation from the previous page, what is the correct answer to this question? Assume that the Earth travels in a perfectly circular orbit around the Sun. Determine a solution to the question of what is the acceleration that the Earth experiences as it travels around the Sun. Once you have calculated the velocity of the Earth as it travels around the Sun, you can use the centripetal acceleration equation to solve this problem. Test tubes are put in a centrifuge and spin in a circle of radius at 20 centimeters. How long should it take a test tube to complete one revolution if you want the contents in the test tube to experience a 25 g acceleration? Recall that an acceleration of 25 g means that it is 25 times the acceleration rate due to gravity. If we assume that value to be approximately 10 meters per second squared, then the acceleration required is 250 meters per second squared. A direct plug into the equation for centripetal acceleration will give you a value of an approximate time. An object traveling in a circular path at constant velocity does indeed experience an acceleration. This acceleration is toward the center of the circular path at all times. The velocity vector for the object is always tangent to the circle. Note, the expressions from straight-line kinematics cannot be applied to the motion of such an object. Since Newton's second law is about unbalanced forces, then you must have an unbalanced force to cause a centripetal acceleration. We will call this unbalanced force a centripetal force. Here is an illustration of a classic physics course experiment where you determine the force needed to keep the swinging rubber stopper in a circle of known radius. The experiment involves spinning the swinging rubber stopper in a horizontal circle above your head. If you swing the stopper at a fast enough speed, the 100-gram weight will counteract the force needed to hold the stopper in place. The 100-gram weight is the centripetal force. Likewise, you can see that the Earth is supplying a centripetal force to keep the Moon from flying off of its orbital path. This is a gravitational force, which is also called a centripetal force. Remember that the centripetal force is directed inward toward the center of the circle, while the velocity of the object is always tangent to the radius of the circle. The key to solving a problem involving an object moving with uniform circular motion is to realize that the object is traveling in a circular path and therefore experiences a centripetal acceleration. The net force acting on the object must point toward the center of the circular path. Remember that in your free body diagram you include all of the forces acting on the object. For every force on your FBD, you can point to an object that exerts that force on the object. For example, a normal force is exerted by a surface, a gravitational force is exerted by the earth, tension is exerted by a string, etc. You might be tempted to include a centripetal force in the FBD. Don't do this. The centripetal force is a combination of the forces already included in your FBD. A crate of eggs sits in the middle of the flatbed of a truck as the truck negotiates a curve in the road. The curve may be regarded as an arc of a circle of radius 35 meters. If the coefficient of static friction between the crate and the flatbed is 0.6, what is the maximum speed the truck can have if the crate is not to slide during the maneuver? The solution to the problem is on the next page. Start by drawing a FBD of the crate of eggs. In the y direction, the crate doesn't move, so v sub y equals 0 meters per second equals constant, and a sub y equals 0 meters per second squared. Along the x-axis, there is only one force, so now, since the object is moving in a circular path at a constant speed, we have this. Substituting what is known about the frictional force and the acceleration, we come to this. Follow the path of the equations used and you can see how fast the truck can travel and safely haul its eggs. The truck can travel as fast as 14.3 meters per second around the curve without the crate of eggs moving. If you live near a park that has a merry-go-round, it is sometimes fun to just go and sit on the merry-go-round and get pushed. Feeling the kinesthetic properties of rotation can be a great learning experience too. While you are sitting on the moving merry-go-round, try playing catch with somebody on the same merry-go-round, or somebody standing on the ground beside the merry-go-round. Think about the perspective of what the ball would look like from each of these positions. Here's a problem to try on your own. A merry-go-round turns completely every 12 seconds. 3 meters from the center, what minimum coefficient of static friction is necessary to keep the child from slipping? These are classic 1960s films that have been archived. Professor Humes and Ivy do an excellent job getting you to think about the merry-go-round experience, plus other ideas related to frames of reference. Millions of physics teachers and students have enjoyed these films in the past, and you might consider doing the same. An engineer needs to design a curved exit ramp for a highway in such a way that the car will not have to rely on friction to round the curve without skidding. Suppose a typical car rounds the curve with a speed of 30 miles per hour and that the radius of the curve is 50 meters. At what angle should the curve be banked? In the previous problems, a single force was responsible for causing the object to travel in a circular path. In this case, a component of a force causes the circular motion. In other cases, combinations of forces might cause the centripetal acceleration. A drawing of the situation and the FBD looks like this. The forces are broken into components along the standard axes, so that components of force will point toward the center of the circular path. Now we would write the components of the normal force in terms of the angle. Since there is no motion of the car along the y-axis, v sub y equals 0 meters per second equals constant. This means there is no component of acceleration along this axis. Along the x-axis, the x component of the normal force causes the centripetal acceleration. Substituting for the components of normal force in terms of the banking angle, we get this. Next, we divide equation 1 by equation 2. The necessary banking angle is 20.1 degrees, as was just derived from the mathematical interpretation of this banked curve problem. Try this on your own. An amusement park ride consists of a rotating circular platform 8 meters in diameter from which seats are suspended at the end of a 2.5-meter long chain.